Okay, welcome everyone. Today, Jaiung will tell us about tropical subrepresentations and matroids.
All right, thank you for being here. So today I'm going to present some small observations that I found on these tropical subrepresentations and its relation to matroid. This is joint work with Kalina, Mincheva, and Jeffrey Tolliver. All right, so I should start with how semi-rings can be used in tropical geometry, because the tropical semi-field will play some role in this theory. So semi-rings are used to set up algebraic foundation for tropical geometry. And semi-rings are like rings, but you cannot actually subtract, or you may, but it's not necessary that you can actually subtract. And semi-field is like a field, but you may not subtract. So two main semi-field in tropical geometry is the tropical semi-field and Boolean semi-field. And tropical semi-field, I'm using the underlying set of the zero Boolean numbers together with negative infinity. And tropical multiplication is usual addition, and tropical addition is maximum. So I'm using here a maximum convention, with the negative infinity being the smallest number. And subset consisting of 2 points, 0 and negative infinity, which is denoted by B, is called a Boolean semi-field. All right, so the example of tropicalization, if you use tropical semi-field, goes in this way. That you have an affine variety defined by, for instance, in this case, the polynomial x plus y plus 1 with the valued field k. And the first step is you take, you do the tropicalization for your polynomial. By this, I mean that you switch the classical arithmetic to the tropical arithmetic, and you take the valuation for the coefficient. So here the polynomial is meant to be 0 times x plus 0 times y plus 0. And once you tropicalize your polynomial, then you take this tropical locus, which is the, in this case, set of vectors, where the maximum is achieved twice, and you get this picture. And if you use actually semi-rings, you can actually go one step further to do the scheme theoretic tropicalization, which is introduced by Giansiracusa brothers. And the idea is fairly simple, that if you have this condition that maximum is achieved twice, then you can actually change that condition into what they call it as a band relation. So you can actually check that that condition is same as by looking at the congruence relation generated by this. So you start with x plus y plus 0, and each step you remove one monomial, and then you identify them, and you look at the congruence relation generated by that. And that's going to be the coordinate semi-ring of your tropicalized variety. And by taking t points, you recover the set theoretic tropicalization. All right, so a little bit of a background here. So I was actually interested in developing some theory of equivariant vector bundles, or vector bundles in general in this setting. And in this case, with T, the structure of general linear group is quite restrictive, in the sense that it's a semi-direct product of Sn and diagonal matrices. So there is a split short exact sequence of this type. So essentially, GLN with entries in the tropical semi-field is monomial matrices with entries in here. All right, and if you sort of shiftify this short exact sequence, then you can show that when X is a irreducible scheme over the tropical semi-field, then any vector bundle in this case is a direct sum of line bundles. And in the case of toric, in the toric case, the same goes with the torus equivariant bundles. So it's pretty much disappointing. Yes.
This is not the same vector. This is not the same vector bundles that Kalina or McLagan can use.
So our definition is purely in terms of locally free shift and so on and so on and so on. But if you have toric case, by this I mean that you have monoid cooked up from fan, and then you do the scalar extension to the tropical semi-field. And in that case, our equivariant vector bundle, torus equivariant vector bundle is the special case of Kahn and McLaughlin when underlying Matroid is free.
I see.
So
that's why
it's very special.
That's why you split into a direct semi-prime bundle.
Yes.
I see. Okay.
And I put theorem quotation because I haven't explained anything about what it means by X is scheme over T and so on and so on and so on. But what I'm trying to say, this will show up again, but because of this, some odd phenomena happens in this tropical algebra. And in doing so, one small observation that we could make is that, as in the classical case, equivariant bundle theory over one point spec T is same as representation theory over T. So we started this whole thing as a sort of side project. And to go into representation theory in tropical or combinatorial setting, then I should sort of consider what kind of object that I can use as a vector space. And I have met 3 different mathematical objects which can be used as a vector space in this context. The first one is the most naive one that you can look at free module over T, which is nothing but T to the N. And the second one is the bit algebraic and bit combinatorial, that is tropical linear space or evaluated Matroid. And the last one is finite pointed sets, which also called F1 vector spaces, because in the field of F1 geometry, people started using this finite pointed set as a replacement of vector space. And idea is fairly simple without addition and scalar multiplication. What it means by a vector space is simply a fixed basis. So finite pointed set here is just a fixed basis. And then the item 2 and 3 tropical Matroid and finite pointed sets are related. There's an adjunction. There's a functor from the category of Matroid with strong maps to the category of finite sets by taking underlying set. And the other way around, if you have a finite set, you can cook up a free Matroid, which is going to be Matroid. All right, so now there is another side note, because before I actually started working on this representation theory of in the tropical setting, I actually started with the Kuiper representation over F1. So Kuiper is nothing but a digraph or directed graph. And then what it means by a Kuiper representation is that you put a vector space at each vertex and you put a linear map at each arrow. And the whole those data is defines Kuiper representation. And to do that with over F1, then what you do is that you replace vector space with a finite pointed set or F1 vector space. And you replace the linear map as a F1 vector space morphism, which is not just pointed set map, it has an extra condition, but it's close enough. And if you do that, the types of theorems, again, there's quotation mark because I actually didn't specify what it means by some conditions here. So types of theorems that you can prove is that if you have Kuiper representation over complex numbers, which has some F1 data satisfying some conditions, then the Euler characteristic of Kuiper-Grassmannian can be purely computed by counting number of subgraph of a directed graph. And this subgraph of a digraph exactly corresponds to the sub-representation in the F1 context. So in a way that Euler characteristic, in this case, you are actually counting F1 rational points of F1 Kuiper-Grassmannian. All right, so, and then there are other papers. So in our case, I replace the vector space with F1 vector spaces, and you could also go for using Matroid. So there's work on tropical Kuiper-Grassmannians. We saw Victoria's talk. And then if you go one step further, noticing that tropical linear spaces or evaluated Matroid is a special case of Matroid over an idle, where idle is tropical hyperfield, and you can go for Kuiper Matroid. So idea is pretty much out there.
What kind of subgraphs do you have to count?
You said the number of subgraphs.
It's something called downward close. So if you have this vertex and this one, and there's arrow, directed arrow, then this vertex should be in your subgraph as well. Okay. So I guess the theorem actually is I found it interesting because in the literature people only consider what's called tree modules, band modules, and so on and so on. But then this theorem gives a way to see other directed graph rather than just tree and band. All right, so let's see what happens if you take the most naive approach of vector space being T to the N. And then if you look at the representation theory of groups over T, then it's pretty much like a monomial representation. So representation in this case is just homomorphism from group G to GRN. And one key observation in this case that one can make is that this homomorphism rho determines G actions on this LV, what we call as the set of basis lines. It's where this guy is the span. And the definition itself actually has a fixed basis B in it, but one can actually prove that this set right here, this guy is independent of choice of B. So whichever base B that you choose, you're gonna end up with the same set of V. And G action is in this way. So G act on each this way. All right. So I guess some of you.
I think it's a little bit too fast. What the basis there means the usual notional basis,
Yeah.
or some tropical?
It's no. It's just I guess it's a minimal generating set, but not in tropical sense.
I guess a semi-module, you mean?
But what is V? V is a real vector space, or?
So I guess
what is V?
it's T to the N.
And B is a minimal generating set.
Yeah.
B as a semi-module.
Yeah. P as well.
And GLV means
G act on each of these, but G act on V here.
So is this like a?
So this is the definition actually.
I permute basis elements and then I rescale them by a scalar. Is this what?
yeah, so GLV is SN semi-direct product T star F.
Here.
No, the general linear group of V.
Mm-hmm. Yeah.
And does my action go like? Does my action go by permutation of the bases?
Right,
By add permutation
So
of entries?
right. So the action makes sense because if you have vector space in this setting, and if you have two different bases, then they are related by just permutation and rescaling. So the action of this is going to be another basis here, and the span should be the same. So it's just a permuting basis. Is it clear or still is it confusing? I try to not to bring semi-links because it always confuses many people who are not familiar with semi-link theory, but it's still introduction, and it's just is it clear now or?
Just making sure this GLN of T is a group. Is it a semi?
It's a group.
Okay, great.
It's the group of n by n invariable matrices with entries in T. So it's
So that T multiplication, it's like sort of a.
yeah, some odd multiplication. Yeah.
Nice, great.
Okay, good. All right. So with this, types of theorems that one can prove is that if G is a torsion group, then there's one-to-one correspondence between isomorphism classes in decomposable representations. I think it's pretty much the story is same as the monomial representations that what one can prove is if you have indecomposable representations of isomorphism, then there's one-to-one correspondence with a pair of a subgroup and a character. So in this case, and up to equivalence if and only if two pairs are equivalent if they are conjugate. But then I guess what we actually proved, well, but then because this is quotient free, remember that we are actually using addition but not multiplication as its group structure, so it's a torsion free. So the character here is irrelevant, so it corresponds to the conjugate classes of H. The second one follows from the first one that if you have so you can show that there is one-to-one correspondence between isomorphism classes of indecomposable representations and isomorphism classes of finite transitive G sets. The way it goes is that if you have a representation, then you send it to the set of basis lines, and then if you have finite transitive G sets, then you pick, and then from here you take H as stabilizer of X, and then from this correspondence you're gonna have a unique indecomposable representation of the isomorphism. Yep.
Does indecomposable in this setting, is there something special about it, or is it just literally you translate the definition?
A classical definition that you cannot decompose as a direct sum of two subrepresentations. And the theorem itself comes from the fact that any representation can be decomposed uniquely of the permutation direct sum of indecomposable representations, which corresponds to the orbit decomposition of finite G sets. All right. And there are some stark difference between this representation theory over T. So I'm stating here in terms of T, but I guess I should mention that the result that I'm stating here is true for any idempotent semifield. Where idempotent means that if you add, then you get the same thing for any choice. All right, so yeah, so there's a stark difference. The first one is that if you look at the regular representation, then it's indecomposable. So it has something to do with this guy having no non-trivial zero divisor. And if G is finite, then any irreducible representation is just one-dimensional. And there is something that can be easily proved, that you choose B, which is not equal to 0, and you look at the G invariant element, then span of Y is going to be the sub-representation of V. But if V is irreducible, then it should be this guy. So it's a dimensional. All right.
What does irreducible mean for semi-rings?
It doesn't have any proper sub representation. So it's the same thing. And there's a problem actually. I think irreducibility here, if you define it as in the classical case, then we get something boring like a vector bundle split as the sum of line bundles. So one may want to come up with some better definition that I don't know what it is. All right, so okay, so now the end of introduction. So what I'm gonna present today. So I'm gonna first review the definition of tropical subrepresentations. And then I'm going to explain matroidal representations, which is the same as group actions of matroid. And then I'm going to give you the classification result of rank 2 and 3. And I'm going to specialize to the case of abelian groups. And then I'm going to generalize these matroid representations to the case of evaluated matroid. All right, so let me briefly record the definition of evaluated matroid. So evaluated matroid here that I'm using is the evaluated matroid M of rank D on this n element set is just a function from the set of the element subsets to the tropical semi-field, satisfying these two conditions that it cannot be identically 0 or negative infinity. And then if you have two sets ST, then they should satisfy exchange condition, but up to this weight function. So if you look at this equation in this line, then you can easily check if you use the Boolean semi-field B instead of T, then this condition here is precisely the basis exchange condition. And from here, one can cook up tropical linear space. So tropical linear space has equation which comes from the evaluated matroid, and it's a tropical locus of these polynomial equations. So I guess I can assume that we are familiar with these two. All right, so as an example, if you take your field to be the field of rational numbers, and if you look at this 2x4 matrix, then by looking at the columns, one gets a uniform matroid of rank 2 on 4-element set. And to make it evaluated, one can use, say, twoetic valuation and define the wave function in this way. So W of ij, you first take the determinant of some matrix consisting of column Vi and Vj, and then you take the twoetic valuation. Then you get these numbers. And then from here, because it's rank 2, you look at the 3-element subsets, 2, 3, 4, 1, 3, 4, 1, 2, 4, and 1, 2, 3, and you cook up these four equations. And tropical linear space defined by this evaluated matroid is the tropical locus of these polynomials. Okay, so now so in the introduction, I explained what can be done and what kind of theorems that we can prove if you use a vector space as t to the n. And now this is the case, what can happen if you use a evaluated matroid. So this definition came from paper of Giansiracusa and Manaker. And what they did is that they don't actually define a tropical representation, but they define a tropical sub-representation. So to do so, you fix first linear representation as we discussed here. And then the tropical sub-representation is nothing but a G invariant tropical linear subspace. And dimension of this sub-representation is the dimension of V, or it's the rank of the associated evaluated matroid. And they proved, as in the classical case, that this precisely corresponds to the fixed point of G action on the direction. Okay. So, and then in some special case, they also introduce notion of tropicalization of representation. So once you have a vector space, classical sense W, and you fix isomorphism or fix a basis, then it's said to be a monomial representation. In their terminology, that the matrix for each G with respect to this fixed basis is your monomial matrix. Then you with this fixed basis, you can use your representation in this way, and they define the tropicalization of this monomial representation to be just taking the valuation for your non-zero entry of your matrix. And then they say the tropical subrepresentation T. So if you start with a monomial representation W, and if V is the tropicalization of W, then they say that tropical subrepresentation T of V is realized by subrepresentation if it comes from tropicalization of subrepresentation of W. Am I still going too fast? I have a tendency going really fast if I get nervous. Yep.
Do you know how common it is for a tropical subrepresentation to be realized?
Say again?
Like, how many non-realizable tropical subrepresentations are there? Like, is it very common? Is it the exception?
I think I have a theorem in the next slide, but they are extremely rare. I mean, I don't have exact, it's not my theorem, it's their theorem, but they are quite rare. It's not like every year.
There's another question.
Yep.
What is the major obstruction in defining just a tropical representation? Like, why do we have to stick for subrepresentation?
So, well, in my case, to be honest, in my case, we look at and we played with T to the N, and we found theorems which we liked, but someone find it like boring. And then you're like, why don't you then move to other types of mathematical structures? And then you're thinking that, vector space or tropical linear space, why don't you look at? And then we found this paper and then we just played with it. And, there's absolutely no reason why you cannot define, although I don't know how to do it. That's why, but I don't know any particular obstruction that is not like, short answer, sorry.
Thank you. That's...
Isn't this more or less equivalent to asking about like defining automorphism groups of evaluated matrix?
That we're sure. Yeah, that's precisely what that is.
And then the second one is like which automorphisms of evaluated matroids comes from like automorphism on the realization of the evaluated matroids or something like this.
I don't know.
Okay, yeah, I don't know.
All right. So, and then what they notice is that, so I guess everything here I wrote, even if I wrote in terms of T, but everything here is true with the idempotent semi-field K. And I guess original paper by Dress and Benzel, they also use this idempotent, they didn't put it as an idempotent, I don't exactly remember, but they didn't simply use the tropical semi-field. All right, so in the case of the Boolean semi-field, then you can, or they proved that in this case, tropical subrepresentation is the same thing as homomorphism from group to the automorphism group of the associated matroid. So in this case, because you don't have any scalar, so evaluated matroid in this case is going to be just matroid. Over B, tropical subrepresentations and group action on a matroid is going to be the same thing. And special case of the monomial representation that one can consider is the regular representation, which is permutation representation. So it tropicalizes, and then with this fixed regular representation as your fixed linear representation, any tropical sub-representation is going to be a matroid on a ground set, for which left multiplication by element of G is a matroid automorphism. So we get this. And then they prove various things, but among those, they prove this kind of theorems. So if you fix a trivial valuation for the complex numbers, and if you have a finite abelian group, then they prove that this group is cyclic if and only if U2G here, I mean, so I guess U2G is just rank 2 uniform on the rank set of G, or not really G.
What do you mean that's when you say that that's realizable?
Precisely, so realizable, it should be something something which has to do with the fixed linear representation. So in this case, you fix regular representation, that's going to be your fixed linear representation. So you fix regular representation, and that's going to be your V here, which comes from the regular representation in the classical sense. So classical sense, regular representation with trivial valuation tropicalizes to, and you're looking at sub-representation here. And you ask whether or not it's coming from something here. Is it clear or? Yep.
So by monomial matrix, do you mean like monomial in this fixed basis?
Yeah. That's the definition that they use, unless otherwise, I don't know what to go for.
Right.
And for all of this, it doesn't matter which K I choose, little K. Little K vanished from that.
So something is realizable. It depends on the valuation and ground fields that you use. But the results that I just presented, they use complex numbers and trivial valuation. And their realizability is under that fixed choice of trivial valuation of complex numbers.
If I change that C to little k,
Mhm.
the definition depends on my choice of K.
Yeah, I think so, yeah. So yeah, these are types of theorems that they proved. So somehow on the right-hand side, you have a matroid with G action, and then on the left-hand side, you have a structure of group. So somehow this theory connects group theory and matroid theory. And they computed examples like this, and then they came up with conjecture that there is only one two-dimensional tropical subrepresentation of the regular representation of Zn, if and only if n is prime. And this conjecture was proved by Marcus and Phillips last year, that they proved that there is one-to-one correspondence between two-dimensional subrepresentations, tropical subrepresentations of these regular representations, regular representation and proper subgroups. And this was our starting point. So we started generalizing the result of Marcus and Phillips to the case of just G sets. So their theorem is about matroid structures on group G, and one can actually go for like this. So if you have a finite group G, and if X is a finite G set, then Matroid structure is called G invariant if it carries basis to basis for all G. And one key observation to classify rank 2 case is that if you have a Matroid without loops, then any Matroid defines this equivalence relation. And loopless condition here is needed to ensure that this equivalence relation is transitive. So with this, one can prove that there is one-to-one correspondence between G invariant loopless rank 2 Matroid structure on X and G invariant non-trivial equivalence relation on X. What I mean by G invariant. So if this is an equivalence relation, and saying that this is G invariant, it's just and the correspondence goes pretty much straightforward way that if you have a G invariant loopless rank 2 Matroid, then you obtain this equivalence relation, which can be shown as G invariant and non-trivial. And the other way around, if you have relation here, then you can define is independent if it's a subset of X and Y, for non-equivalent element X and Y. Then that's going to give you a one-to-one correspondence. And this is generalization of the theorem of Markers and Phillips in this way. So one can make these observations that any G invariant rank 2 Matroid should be loopless because once you have a loop, then G act on G in a transitive way. So every element should be a loop, which can then in that case you cannot have rank 2. And this condition G invariant non-trivial equivalence relation is pretty much the same as in the case when X is G, is same as proper subgroups of G. So our theorem generalizes the theorem of Markers and Phillips. Rank 3 case, I mean, after we actually proved the theorem that I asked my collaborators, what do we mean by classification? Because it seems our classification theorem make the problem look a lot harder. Because I mean, it's so clear. I actually Googled and I asked ChatGPT and so on and so on. What does it mean by actual classifications in mathematics? But I don't know. But this is what it had. So on one side we have rank 3 G invariant Matroid structure on G, and on other side you have a pairs. H is a proper subgroup of G. And this tilde is a non-trivial equivalence relation on this coset, G mod H minus 1, satisfying these two conditions. And if H is a trivial subgroup, then corresponding Matroid is simple. Then it follows from two observations. The first one is that you can actually do the simplification of a Matroid in a G invariant way. So there's one-to-one correspondence between G invariant loopless rank K Matroid on G set E and pairs of equivalence relation, non-trivial G invariant equivalence relation on E. And so I think it's better to just write it here. All right, so how does it go? So this direction is pretty much clear that you use the same equivalence relation. That I mean, this is same if they are identically same, or is a circuit. And then, M tilde is just simplification of M, which is going to be matroidal. And the other way around is pretty much also straightforward. That if you let pi be the Gaussian map, then you can define I is independent if and only if I is independent. And that's going to give you this one-to-one correspondence. Oops. And then there's another lemma that is used to this prove the theorem, is that in the case of simple rank 3 G invariant matroid on the coset G mod H as a G set, and it corresponds to this data, that non-trivial equivalency relation on G mod H minus 1, satisfying these two conditions, 1 and 2. And also the correspondence is quite straightforward, that if you have simple rank 3 G invariant matroid on then in this case you define if X is 4, I guess I should use the Gaussian notation, on X is dependent. And then one can check that this is actually an equivalency relation. And again, simple condition is needed to ensure that this relation is transitive. So you get, in this way, non-trivial equivalency relation on this coset, which satisfy conditions 1 and 2. And the other way around is pretty much the same. So in this case, B as a basis. If and this condition. And if you combine these two lemmas, then you get this classification theorem for rank 3 case. And starting from rank 4, I think we haven't even tried, but I think it's getting a lot more difficult than you see that already rank 3 case is a lot more complicated than rank 2 case. And in general, I have no idea how it can be done. All right. So now if we specialize ourselves to the abelian group case, then we initially had theorems like this, and I'm not going to go over this, but these conditions on prime numbers and so on is just to ensure that we have non-trivial equivalency, G invariant equivalency relation on ZP, as in previous rank 3 theorem. And when you're actually proving theorems like this, we realize that we can actually come up with some better definition which can explain the proof technique. So we introduced what's called distinct difference system of abelian group G. This is just finite collection of subsets which satisfy this condition 1, 2, and 3. And conditions 2 and 3 are pretty much straightforward, that if you have two different subsets, then they should only overlap at 0. And they should contain at least 2 elements. And then the first condition is meant to be if you have the same difference, then you should have the same pair. And I think I don't know about applications of that. And this definition, after we found, we thought that this one looks quite natural. And then we realized that in the case when collection consists of just single subset, then it's called a modular volume ruler. Oops. All right, so this is just an example. If you choose n to be an odd natural number, and if you choose a k and u, and define the single set S consisting of these 3 points, and these are all possible differences, and you want it to be exactly different, and this condition is true when you choose k to be not equal to these numbers. All right. So yeah, okay, so now if k is a natural number greater than or equal to 3, and if G is finite abelian group with n is k elements, then if you fix a distinct difference system S1 through SL, and if you define a subset of G to be basis, if it has precisely k elements, and if it's not a translate of a subset of some Si, then this yields a simple rank k G-invariant Matroid structure on G. And if you specialize your group to be the cyclic group of prime order, and if you look at the rank 3 case, then you can actually show that all simple rank 3 G-invariant Matroid structure arises in this way. And this is pretty much the idea that if you have this distinct difference system, then it's going to give you an equivalence relation as in rank 3 theorem. So for any index I and element Z in Si, you cook up this set T sub iz, which is just a set of differences. And then if you have this set of differences, then it's going to give you an equivalence relation in this way, X and Y are equivalent if they are same or they are in the same TIZ. And so, which means that if you have a distinct difference system, then you get a rank 3 Matroid, and the condition ZP and rank 3 is needed to make sure that any equivalence relation in the classification theorem arises in this way. All right, so now this is the one that I had in my previous slide. So over the Boolean semifield, tropical subrepresentation is nothing but a group homomorphism from group to the automorphism group of Matroid. And what we tried is to generalize this to the case of evaluated Matroid. And the first question is, how can we define an automorphism group of evaluated Matroid? And there might be other choices. We tried to find from the literature, but we were not, well, it may be the case that we didn't try really like hard, but we were not able to find much of any information about the automorphism groups of evaluated Matroid. So this is the definition that we came up with. So we say that element of the symmetric group Sn is a weak automorphism if you can find some map tau from n to t satisfying this condition. So it's going to send a basis, weight over basis, to weight of another basis up to some twist of this map tau. And this notation here is the group of weak automorphisms. All right, so now so this map pi here is that we had previously showed exact sequence where we were able to write GLN of T as semi-direct product of Sn and diagonal matrices, and pi is the projection from that to Sn. And for any tropical linear space phi, we use automorphism of phi as n by n invertible matrices, which maps precisely phi to phi. And what one can prove so is pretty much we have this shared exact sequence. And here there's a weak automorphism group of evaluated matroid. And what theorem says is that here we have automorphism of corresponding the tropical linear space, and this is shared exact sequence. Space shared exact sequence. And all right. So, and what can actually go as quotient construction to understand the weak automorphism group. So QM here is like coordinate semi-ring of your tropical linear space, which is cooked up from this bunch of polynomials. They produce what Giansiracusa brothers called as a band relations. Then that's going to give you this module QM. And with this, if the underlying matroid of evaluated matroid is simple, this condition is essential, then there's an injection from automorphism group of QM viewed as a module to these n by n invariable matrices. And if you take the projection, then it's precisely the weak automorphism groups. All right. Now, to finish almost. So if n is a evaluated matroid, then we call a weak G action as simply a homomorphism from G to the weak automorphism group of M. And two weak actions are isomorphic if they are conjugate, and two tropical sub-representations are isomorphic if also they are conjugate. So this is same as the classical definition. And with this, what we were able to prove is that if you have a finite group, then there is nice correspondence between isomorphism classes of tropical sub-representations and isomorphism classes of weak G actions. So the proof actually used a bunch of things in the paper. So I don't think I can actually explain it here. And I guess that's it. Thank you.
Questions?
Yep.
I noticed this was off-rammed in terms of semi-rings. Is there a similar picture if you look at like the tropical hyperfield sort of picture?
Which picture?
Like just sort of setting up some notion of representations for like hyper things instead of semi things.
Tropical hyperfield, if you use tropical hyperfield as a hyperfield, not as an idle, then you have a problem with matrix multiplication that is going to be multi-valued. And I don't know how to deal with that. But if you look at it as a like an idle, as in like Baker and Rothschild, then it may be doable. And the whole thing, I think there is no actually counterpart of tropical linear space for the matroid over idles. But I think the whole story can be done in terms of quite straightforward way by using matroid over idles. Yeah.
I think some people believe that the GLN should not be a group, and that's more interesting. Is there like a strong something that you're not telling us because you told us a bunch of weak morphisms and weak?
That's actually a good question, and that's
Why do you tell us like?
because evaluated matroid should have some scalar component, but our definition of automorphism here only use the permutation.
But
And
you could have included the scalings too
we
as part of the
finished paper and then later sort of realized that in the Oliver's paper on Cuba matroid, they introduced notion of morphisms between matroid over idols. And then that that morphism, I think, is actually, and I think that's also the same definition Victoria used in a paper. And but this definition, as in like so in the paper, what we essentially have for is that there's a projection to this. I don't think this answers your question, but should answer. My collaborator named it as a weak, and I didn't have any objection, so we went for weak. And they define this in terms of some sort of some monomial matrices, sending vectors to vectors or cofactors. I don't exactly remember. And yeah.
We had one more.
Yeah.
In your introduction, one of your motivations was this theorem about quiver representations over C. Can you just say briefly how that's related to all of this other stuff?
Oh no, it's not related. It's not related. I hope that I can find by doing so. So in the quiver representation case, I found it actually amusing to do this interpretation that like all the characteristic of Kuiper-Grassmannian can be done by counting sort of F1 rational points. That is sort of the underlying theme of F1 geometry. But we don't have such application in tropical subrepresentations and its relation to Matroid yet. I'm trying to find something that can be done in like this. Yep.
What is an interesting group action on a matroid? Like, if you were to pick an interesting example for you. Maybe one such dispersal for things geocodering.
I don't have a good answer to that. I only played with examples like quaternion group or like ZNCP is something that I get my hands on. But even with yeah, so sorry, I don't have a good answer.
Okay, if there are no more questions, let's thank the people one more time.